So just as I suspected, I definitely ran out of time with only 15 minutes. So I'm going to have to break the section up into several videos. So this is going to be 4.1 part 2. And in this section, I'm going to talk about some of the characteristics for the graph of a polynomial function and also the leading term test. And again, I will scan these notes so that you can have a copy of these notes. So there are some things about the graph of a polynomial function that you can always expect to see. And it's 3 things in particular. For polynomial functions, the graphs are always smooth. And I'll show you an example for each of these in just a second. They are continuous. And they have a domain of negative infinity to positive infinity. Domain is the term we use to describe the set of values we're allowed to plug in for x. And by using the interval notation negative infinity to positive infinity, that means we can plug anything we want in for x, any real number. Because the only operations we ever see in a polynomial are exponents, and then multiplying or dividing by a real number, and then adding and subtracting the pieces. So we can raise anything we want to an exponent. Back in chapter 1 and chapter 2, when we were really talking about domain a lot more, the things we had to be careful of are the type of functions we had to be really careful of in restricting their domain were rational functions, which are functions that have x in the denominator, and radical functions. And polynomials are not allowed to be either of those. So that means we don't have any problems. We can use anything we want for x. So this is an example of a polynomial function. And it's going to look pretty nice. But you'll be able to really see the difference when I show you the non-polynomials. So it is smooth, it is continuous, and the domain is negative infinity to positive infinity. So that means I'm going to start all the way on the left. And I'm going to end all the way on the right. And I connected the entire thing with one curve. That made it continuous. If at any point I had to stop and pick up my marker and put it down in a different spot, that would create a hole or a gap in the graph, and that's not continuous. It's smooth because there are no sharp corners. So this is an example of a polynomial. It is smooth, continuous, and goes off both sides of the graph. Off to the left, off to the right. So a few examples of things that are not polynomials and what their graphs would look like. And you have potentially seen all of these graphs before. This first one is a variation of the absolute value graph. And this graph has a sharp corner. So it is not smooth because of that sharp corner. An example of a graph that is not continuous would be a piecewise function, where we're coming up and having to stop the graph and jump somewhere else to restart it. So anytime you have to pick your pen or pencil or marker up and move it to a different place to keep drawing, that is a discontinuity. That's a spot where your graph is not continuous. So this right here is not continuous. And then one more real quick, an example of a graph whose domain is not all real numbers, negative infinity to positive infinity. This is a variation on our square root graph. And this graph starts at a particular number and then goes off to infinity. it does not go off the left side of the graph. So we don't see an arrow on the left-hand side. We only see an arrow on the right-hand side. So the domain for this function is restricted. So that's a problem. And this would definitely not be a polynomial. So I'm just going to say that value there is a, just to give it some random value. I'm sorry, this is out of focus. So the domain for this graph would be a to infinity, because the lowest x value is a, and then it goes off the right-hand side of the screen, which is positive infinity. So those are the three examples of things that we would never see in a graph of a polynomial function. A nice, smooth, continuous graph that goes off both sides, to the left and to the right. So how exactly our graph goes off to the left and to the right depends on the leading term. So we have something called the leading term test. Excuse me. And the leading term test says to take your polynomial, and I'm just going to keep using the same format we've already seen now that we've explained it, and hopefully it's not quite as nasty looking. And what this graph does on the left side and the right side depends solely on our leading term. So our leading term is a sub n times x to the n. So there are two characteristics that we want to be able to identify in that leading term that will help us decide the end behavior of the graph. So end behavior means what is happening on the far left, and that's as x goes to negative infinity, and the far right, and that's as x goes to positive infinity. What is the graph doing? Is it going up or is it going down? And there are two things we're going to look for, and they could both be broken into two categories. So we're going to look at this leading coefficient, and whether that leading coefficient is positive or negative is going to be part of our test. And then we're going to look at the degree, and whether that degree is even or odd is going to be the other part of the test. So if a sub n, it could be positive or it could be negative. The degree n could be even, like it could be 2, 4, 6, 8, 10, or it could be odd. It could be, the biggest power could be 1, 3, 5, 7, 9. So again, the degree is the degree of the polynomial, the biggest exponent in the entire polynomial. We just need to know whether it's even or odd. Now, the easiest way to remember this is start with your coefficient, because it's written first anyway. The sign tells you what the right-hand side is doing. So if the sign of your coefficient is positive, that means the right-hand side is going up. If it's negative, the right-hand side is going down. Positive, right-hand side going up. Negative, right-hand side going down. So the sign of your leading coefficient tells you what the right-hand side of the graph is doing. Positive means up, negative means down. Then to decide what the left-hand side is doing, we're going to look at the degree. If the degree is even, then the left is the same. So here, if the right went up, the left goes up, because even means the same. If the right went down, the left goes down, because even means the same. If the degree is odd, that means the left does the opposite. And an easy way to remember that is they both start with O. Odd power means your two arms of your graph do opposite. So if the right-hand side goes up and the power is odd, that means the left-hand side goes down. If the right-hand side goes down and the power is odd, that means the left-hand side goes up. And there are some simple example functions that we can use to help us remember this that we learned back in chapter 2 when we did our transformations. X squared and negative x squared. So the regular old parabola graph, that has an even degree and a positive coefficient. And that graph, both of the arms go up. When you throw a negative in front of it, it flips it, and both of the arms go down. So negative coefficient, even power. Negative coefficient, even power. Looks kind of like this. For our other two graphs with the odd, you can think of the x cubed graph. And what happens with that one? So regular old x cubed graph looks kind of like this. Up on the right, down on the left. But if you throw a negative in front, that flips it. And it'll go up on the left, down on the right. Now, I've got these scribblies in the middle because we have no idea what any of these graphs are doing in the middle yet. This leading term test only tells us the end behavior, what our graphs are doing as they go off the left-hand side of our graph and the right-hand side of our graph, or on the calculator off the left-hand side of the screen and the right-hand side of the screen. So the sign of the leading coefficient tells us what happens on the right-hand side. And then the degree tells us how to figure out the left-hand side. If it's even, it'll do the same. If it's odd, it's going to do the opposite. And let's do a couple quick examples of this. So the directions are just going to be to find the end behavior, and I like to describe it just with a picture, just like the pictures we had in that table I just showed you. So if we have f of x equals negative 3x to the fourth plus 2x cubed minus 5x plus 9. To find the end behavior, the only thing we need is the leading term, which is negative 3x to the fourth. And we need to know two specific things. From the coefficient, is it positive or negative? And this one is negative. Remember, that tells us what the right-hand side is doing. And the degree, is it even or odd? And ours is even. Even means left-hand side is going to do the same. So just to give us a real quick idea of what this graph is doing, because the leading coefficient is negative, on the right-hand side we're going down. And because the degree is even, the left-hand side is doing the same thing. Now we have no clue what's happening in the middle. We don't care about that right now. We just want to know what's happening on the ends. So this one is going down on both sides. And one more quick example. Let's do 9x to the 7th plus 2x to the 4th minus 3x plus 1. We want to know the end behavior of this graph, and the only thing we care about is that leading term. So that leading term has a positive coefficient, and that tells us what the right-hand side is doing. And it has an odd exponent, which tells us the left-hand side is doing the opposite. So on the right, positive means up. On the right, I'm going up. Leading coefficient is positive. That tells me the right-hand side is going to the positives. It's going up. And then because the exponent is odd, that tells me the left-hand side is doing the opposite. So the left-hand side is going down. We don't know or care what's going on in the middle right now. We just want to know what's happening on the ends of our graph. On the right, we're going up. On the left, we're going down.